we can look for those sorts of chemical or other sources of energy that life can need. And if we find these three things, that's kind of a good agreed upon list that you could declare you found a habitable environment. So how do we go find those things? You build a really cool rover. So this is a car-sized rover. Shoebox that was in 1997 called Sojourner, and that was the first demonstration of being able to drive robotically on another planet. And then followed those in 2003, 2004 with a twin set of rovers called Spirit and Opportunity. And Opportunity is still going today, way outlived its warranty. We're hoping to do it well, but it's been going now for 14 years and 5,000 Martian days. And now that's about a size of a golf cart. And then you got to Curiosity because we have a set of instruments and capabilities that required this big rover. And namely, it's of course we want to drive around like the other two rovers did. But the key thing that we do differently from any rover that's gone to Mars before is drill into rocks. So we have this 6-foot robotic arm, and we have at the end of that robotic arm a drill. And the reason we have that drill is because in order to figure out if those key chemical ingredients for life are there, in order to understand how much water was there and what it did to the rocks, you actually have to sample that material and put it into laboratories and run laboratory experiments to do the quality of science that we want to do. So the rover is this big for two reasons. It has to house this big jackhammer drill, and it has to have a whole front end dedicated to these laboratories. So the rover was built around the capability to drill, get material, powder that you create with the drill, drop it into some laboratories on the rover itself, and run these experiments. So we're doing some pretty sophisticated stuff with this rover, and that's a lot of what led to its size and its complexity. Because you have to design a drill that can work dozens of times without ever being able to clean it, lubricate it, anything. You got to run chemistry experiments without ever being able, again, to clean something or unclog something or all those things you would easily do in a laboratory on Earth. Take something apart, clean it, put it back together. You can't do that. So a lot of the engineering challenge for the science of this rover was to design those systems that can operate 100 million miles away for as many years as we can and do many experiments without ever having a human being able to service it. We also have a whole bunch of other instruments. I won't go through all of them, but we have cameras that, of course, look around and take all of our pictures. Another camera on the end of the arm. We have the drill I mentioned, the laboratories in the front of the rover. We have a weather station. We try to get as much as we can out of these missions by putting a whole bunch of different sensors and experiments on them. One of the coolest things we have, though, is this laser. So if we see anything living on Mars, we can kill it. So we have this laser. This is a really neat instrument because we can actually vaporize little bits of rock and soil on the surface of Mars, and those sparks we can observe with our cameras, and we can look at the color of the spark in particular. So this is like a classic high school experiment. You put some substance in a flame and see what color it turns, and that tells you what is inside what it's made out of chemically. So by shooting with this laser and creating a little spark, a bit of plasma, we can image that with a spectrometer, look at the wavelengths of light that are emitted, and actually figure out from up to 20 feet away what a rock or soil is made out of. That helps us because then we don't have to go drill every little thing that we find. So instead, we're able to do this remotely, and then if something really stands out, we can then drive up to it, put the arm on it, check it out, and if it's really exciting, then we can think about drilling it and sampling it. Here's what it looked like when we were making it. I'm a scientist, of course, so they don't let me anywhere near it. These are all the engineers who built it, who just are, complete magicians at what they do. And they were able to, design and build all this and then it was fabricated, and put together in a clean room, because we're actually doing some very sensitive chemical experiments in those rock samples. So even, the grease from a fingerprint would throw off our measurements if we're trying to look for organic molecules. So the entire Curiosity rover has never seen a human fingerprint. It's all been assembled with these in a clean room environment with everybody wearing bunny suits and keeping it as clean as we possibly can. This is actually the day that it drove its first, it took its first steps, so to speak. So, here's sort of where it lives now. It's kind of a lonely place, but this is a little introduction to where we ended up. We had to choose somewhere to go with this rover that we could conduct these experiments. So that's another big challenge for the science team. In addition to designing all these experiments and figuring out how to have that habitability, another unique thing is that Mars is about it's like if you So, where would you go if you had one chance to answer an important question about Earth? Where would you send your one rover that could rove, 10 miles or so? Who knows, right? And it's a tough question. It took us about 6 years to answer. So we scoured the surface of Mars using all the satellite data that we've been able to accumulate from the orbiters that are around Mars, like this one. And had a lot of contentious meetings where we brought scientists together, and everybody threw out their ideas, and other people said they were wrong, and that's about what we did for 6 years until we narrowed it down from 60 landing sites to 30 to 10. We had a big meeting where we got to 4, and then we went to 4, from 4 to 1 on a very momentous day about a year before launch, and we ended up with this site called Gale Crater right here. And one thing you can see that's even from this picture that's a little unique about Gale is that it's not empty. It's got a mountain in the middle of it, and that mountain is what drew us to it. So here's Gale Crater, about 100 miles across, and it's a 3-mile deep hole in the ground on Mars. Craters like this are formed like they are on the Moon, where a giant asteroid or meteor hits the planet, huge explosion, and dirt's ejected out, and then you're left with this empty crater. So they shouldn't have a mountain like this in it. Sometimes they have a little peak in the middle like this. That's probably there from the original impact. But all this stuff got here later. And what we were able to see when we looked with the orbiters at Gale Crater is that this is a mountain of layered rock, which is also telling us that it's not a volcano. It didn't form with the original impact. Layers of rock built up over time and filled this crater. And that immediately got us thinking that, that you could either do that from wind or you could do that from water. And some of the layers were we could even tell this from orbit, some of the layers were made out of minerals that form when Martian rock interacts with water, specifically things like clay minerals. Clay minerals form when volcanic rock interacts with water over some period of time. It gets weathered down into a clay, and we see some of that in this mountain. So 2 things attracted us. 1, the evidence that there was water involved in whatever process brought this sediment into the crater. 2, that there was a 3-mile high stack of layers. And to a geologist, that's really wonderful because it means that a lot of that stack. You don't build up 3 miles of sediment overnight. So just like if you were to go to the Grand Canyon and start at the bottom,